Chemistry. This is the Unit 1 Important Information Part 6 video lecture. This will be on photoelectron spectroscopy. I've covered a bit of this in class, so I'm going to try and make sure I go over it a little bit and then get into some sample problems. So photoelectron spectroscopy kind of just helps us illustrate electron configuration. So we've already been able to write electron configurations, like for example, magnesium. Magnesium has 12 electrons, and so the way that I would write its electron configuration would be 1s2, 2s2, 2p6, 3s2. That's great. And we know the order from previous lectures and notes. But chemists were able to figure out this electronic configuration by something called photoelectron spectroscopy, which is PES for short. And so what is photoelectron spectroscopy? Well, energy is hit onto atoms. So it's an experimental technique to determine the relative energies of electrons in atoms. We use high energy radiation to remove electrons from an atom, right? So E equals h nu. Remember this equation, H is equal to 6.626 times 10 to the minus 34th joules times second. Nu is the frequency, which is typically in per seconds. That's going to be the frequency of light. We typically have to go with high energy, so probably like wavelengths of like 1 to 200 nanometers, like lower than any of the visible spectrum. We really have to go higher than visible light, like UV, or even or a little bit higher than that, UV light, to kind of emit electrons. Okay, they're located in different shells that we know. It's important to know that valence electrons, which are the electrons that are in the outermost shell, are the easiest to move. So like if I had 1s2, 2s2, 2p6, 3s2, like the magnesium here, the outermost shell is the highest energy level. This is the valence shell for magnesium. So just keep us there. The valence electrons are easiest to remove, and that's because they have less attraction to the nucleus. The core electrons, which are going to be on the inside, so I'm going to try and color-code it here. Core electrons, which are on the inside, they are harder to remove. They are more attracted to the nucleus. They're closer to the nucleus. It's going to require more energy to remove them. So just keep that in mind as we look at photoelectron spectra. All right, the energies of the electrons in a given shell can be measured experimentally with PES, photoelectron spectroscopy. And here is an example of a graph, and I wrote some things here. So here's what the graph will look like. It'll look like these peaks, and there's like different heights of these peaks. The position of the peak, left to right, so the position of the peak, left to right, is related to the energy of the peak. Be careful. Higher energy is more to the left. Lower energy, the position is the energy, the lower energy is to the right. So these peaks over here to the right, like the 3s, the 2p, and the 2s, those are going to be lower in energy than the 1s. And then the height of the peak, up and down, the height of the peak is going to be related to the number of electrons in each shell, or each orbital. So that is going to help us get these different peaks that are going to connect to the electron configuration. We kind of like to make a note that like maybe all the way over here is our nucleus. And then these different peaks here are like the different shells, kind of like from the Bohr diagram. And the farther away they are from the end here on the left, the lower in energy they're going to be. So I'll kind of just erase this. I kind of just made little markings here. And so we're going to see that if I were to read each peak, the first peak is always going to be the 1s peak. Then after that's 2s, then 2p, then 3s. And we know the order: 1s, 2s, 2p, 3s, 3p. Fortunately, in electron spectroscopy, we'll see, in photoelectron spectroscopy, we'll see 3d, then 4s. This is what it will look like, but mostly for AP, you'll probably just have to know up to 3P. We'll see examples of 3D and 4S later, but this is the order that they will show up. And so from here, I'm able to identify what element it is, right? So this peak is the 1S, then it's the 2S. Look at how high this peak is. It looks like it's about 3 times as high. This is the 2P, that has 6 electrons. Then the next one is the 3s. The element that would have this as the electron configuration, as we showed earlier, this would be magnesium. Now, there are 2 ways that I could know this if I knew the electron configuration of magnesium was such, or I add up the superscripts. 2 plus 2 plus 6 plus 12, plus 2 is 12 electrons, which must mean that this is magnesium. And then what's important to know is that this 3s is the lowest in energy, and that's because probably it feels a small Z effective, which is effective nuclear charge from our previous lecture. This 1s is the highest in energy, and that's because it feels a full nuclear charge. It is right next to or on top of the nucleus, so it feels all 12 of those protons. This S2 peak is probably only feeling a +2 effective nuclear charge, and we've calculated that in class. Another note, look at the units here. The binding energy, which is the energy, oops, sorry, I'm zooming in here. This is just the energy required to keep the electrons in the atom. Energy required to keep electrons in the atom. The binding energy is in mJ, megajoules per mole, and 1 megajoule is 10 to the 6th joule. So if I had 50 megajoules, if I multiply by 10 to the 6th, I will get 50 times 10 to the 6th joules, or 5 times 10 to the 7th joule. That's how I convert between megajoules and joules. And then, of course, I could go backwards. If I had 5 times 10 to the 6th joule, if I divide by 10 to the 6th, that's going to be giving me 5 megajoules. So just quickly showing that quick conversion. All right, so that is a quick little rundown. We did a little bit of this in class, but I'm doing it here now. That's how we read each peak. From left to right, it's 1s, 2s. So from left to right, it's 1s, then 2s, then 2p, then 3s. The height of the peak is going to be equal to the number of electrons. If this peak was half this height, it would probably only be 1s1, and then I'd probably stop there. But that's not the case here. Let's do some more examples. So let's look at the sample problem. Which of the following elements might the spectrum represent for sample problem 1 here? Well, this first peak is going to be 1s, this is going to be 2s, and this is going to be 2p. Now, the height of each peak is how many electrons there are. It looks like it's going up by 1, 2. This is probably 2s2. This goes up by 2, so probably 2s2. This goes up by 1, 2, 3, 4, 5, 6. This will be 2p6. What element has 1s2, 2s2, 2p6 as the electron configuration? Well, that's 10 electrons. The element that has 10 electrons would be neon. That would have to be the correct answer here. So that's just quickly how we would look at a photoelectron spectra, get a quick electron configuration, and then identify an element. Let's do another one just to make sure that we're getting the hang of this. Number 2, given the spectrum above, identify the element and its electron configuration. Well, of course, the first one is 1s, then 2s, then 2p. This is going to be, 3s. And then after 3s, we got 3p. That's the order. Now I'm going to identify how many electrons are going in there. It looks like it goes up by 2, so 1, 2, 1s2. This also goes up by 2, 2s2. This goes up by 6, 2p6. This goes up by 2, 3s2. This goes up by 1, 3p1. The electron configuration is 1s2, 2s2, 2p6, 3s2, 3p1. That's 2, 4, and 6 is 10, plus 2 is 12, plus 1 more. We need an element that has 13 electrons. If I look on the periodic table, that is aluminum. Aluminum, a neutral atom of aluminum, would have 13 protons because the atomic number of aluminum is 13. We reviewed that in class. And that, if it's neutral, it would also have 13 electrons. So the correct answer would be B, aluminum. All right, I'm going to set us up for some tougher thinking questions, and I'll leave it up to you. Question 3 says, looking at the spectra for sodium and potassium below, which of the following would best explain the difference in signal intensity for the 3s electron? So these peaks are the 3s of potassium, and this is the 3s of sodium. And it already kind of says, I know there's a lot of writing here. I put a little bit of information here to help you out. To remind you, potassium has 19 protons, sodium has 11 protons. What's also being told is that the 3s in sodium is lower in energy. That's why it's all the way to the right. I'm sorry these numbers kind of got jumbled, but what it's saying is the 3s of sodium is lower in energy. Why? Why would the 3s of sodium be lower in energy than the 3s of potassium? And the only hint I'm going to give you is that potassium has 19 protons in its nucleus. It's atomic number 19. And sodium has 11 protons in its nucleus. So I'm going to give you that hint there. Then for number 4, it says, which element could be represented by this complete photoelectron spectra? We got to be careful. These peaks are a little bit longer. It looks like every 2 bars is 1 electron. So this is 2 electrons. So I'm telling you that this first peak is 1s2. That means this peak is 2s2. I want you to figure out what this peak would be. I'm going to set you up a little bit. And then with this peak and this electron configuration, you could probably figure out what element it is. And then finally, to end, I want you to think about doing sample AP style questions 1 and 2 and sample AP style free response questions 1 and 2 on your own for this. So that's going to end this lecture on photoelectron spectroscopy. Again, you're going to be doing the rest of the sample problems, and then just to remind you, the way that we read the peaks, 1s, 2s, 2p, 3s, 3p, lower in energy to the right, higher in energy to the left. The height of the peaks is the number of electrons. So that is photoelectron spectroscopy.